you look at this term again, and that is 1 minus omega, in this case omega r, that is excitation omega n square, right? And noting that omega n is k over m, and this is 1 minus so essentially denominator is expressing dynamics due to k and m and c, because zeta is c over cr, and the cr is square root 2km c, and that is 2m omega m over c. So denominator actually it expresses how we amplify due to the mass-free Dashba system. And this is first. Okay, let's draw this. I owe you $7. I have to buy a box of oranges. Okay, let's try this. And the zeta is opposite. And interestingly, the phase difference is exactly the same as the phase difference we have for following excitation case. Okay? And the phase difference with other system too. The phase difference is the same. Why? Why? Let's see. Okay, let's look at the response with respect to R, that is the ratio between excitation frequency omega R and natural frequency. And we want to see this mx divided by m. This is 1. When R goes to 0, small and small, this rapidly decays as R square. And what about when R goes to infinity? Okay, this is proportional R square. When R gets bigger and bigger, this is smaller than R to the 4th. And this is, because R is much, much greater than 1, therefore 1 minus R squared to the square is simply R to the 4th. The square root of this is R to the square. Therefore, when R goes to infinity, this approaches to 1. Okay? So this is 1. And R go to infinity. Independent to the zeta, all curve has to approach to 1. Okay. That has nothing control the amplitude. That makes sense? Because let's see what's going to happen as a response using phasor diagram. This is when omega gets large and large, this becomes big. But omega scalar, that expresses the inertial force going this way, and therefore the response is dominated by the inertial force, because inertial force is proportional to the omega scalar. The response is independent to damping, as we can see from the phasor. Okay, so what I'm commenting you now is do not just look at the magnitude and phase diagram, but you must see the physics using other means that we provide you as a handout. For example, this geometric means to look at the response. The phasor does not well express the magnitude precisely, but roughly expresses the physics. Okay? When zeta equals 0.1, it approaches 2. Finish. Now, why we have such a big excitation, even though as he commented, even though we have a very small mass, that mass is small compared with before. Because of what? Because the excitation is proportional to the mass.
Before you go on, you know when eta is really high, does it ever approach one from the below, the lower side?
You got two oranges. I owe you one orange, right?
Last time.
Last time. So omega R square is very important. And when you have sulfur, Korean we call it antiphon, you have a mode of vibration body, you have vibration body, right? You feel some excitation, right? Very small vibration, but you can hear it. You can hear the vibration, right? And you want to have a amplifier to give you big vibration, right? So that you can sense it. Especially you have a very, very high